We talked about polars in AP Prep, but it's been a long time, so I'm going to kind of come from a position that I'll assume no previous knowledge, and we'll try to take it from the beginning. So the idea is we're familiar with X and Y coordinates, and we have an X-axis and a Y-axis, and we know that to get to this point, we go over on the X, whatever we're told to do, and then up on the Y. So that works fine, and that's unique. There's a unique set of coordinates for any point in the plane, and every point in the plane has a unique set of coordinates. But as we'll see, there's some advantages and some power in doing this a different way. Instead of thinking of an XY axis, we'll think of this, which we call the origin when we're talking about X and Y's, is also known as the pole when we're talking about polar coordinates. And we also think of this as being the positive x-axis, which it is in rectangular, but it's also known as the polar axis when we're talking about polar coordinates. So the idea is we can also think of getting to this particular point by going a distance r from the pole and through an angle theta. And so this r and theta is an equivalent way of naming that point, of identifying that point in the plane. So let's do some examples, and then we'll talk about maybe some of the, I guess you could think of it as a drawback. So if we are given the point in polar coordinates that's 2 pi over 3, we think of swinging through, as we did in trig, we're going to go positive as a counterclockwise, and so we're going to go counterclockwise an angle of pi over 3. So here is our angle pi over 3. And then we decide whatever we think 1 is. So if I think of this as being 1, then I go a distance of 2 on that angle, and that is the point that we're talking about there. And we can think of it either as a point, just that little dot. A lot of times we'll draw it kind of like a vector, but it's interchangeable. So in a similar fashion, one of the tricky parts is when the r is negative. So if we look at an angle of 3 pi over 4, that's going to be in quadrant 2. But if our r value is negative, that shoots us back through the pole a length of 1 along that angle. And so the point -1, 3 pi over 4 is actually down here in quadrant 4. So that whole idea of a negative r takes a little bit of getting used to. We can also think about negative angles. We will switch at various times in between degrees, angles in degrees or angles in radians, so we'll be flexible there. So a negative angle means we're going to go clockwise, and we'll go at an angle of 45 degrees, and I'm going to say there's 1, 2, 3, and so that would be our point there. That's at 3, -45 degrees. Now, let's come back for a moment to this one we talked about right here. Now, whereas ordered pair in rectangular coordinates is unique, that's the one and only representation of that point in rectangulars, there's an infinite number of representations in polars. So we could think of going through an angle of pi over 3, but we could also go around the circle. There's 2 pi plus another pi over 3, would make that 3/3 plus 1/3 is 4 pi over 3. 2 would be that very same point. And likewise, there's no reason we couldn't go around in a negative direction. And so that would be, let's see, 2 pi is 6/3 minus 1/3 would make that a negative 5 pi over 3 and still be a positive 2 for the r value. And that also would be that same point. But we could also imagine, now let me get a different color here. So I'm going to go back to yellow. So we could imagine coming down through here. And so now we could, on this angle, we could do a -2. And so this angle would be, since the reference angle there is pi over 3, that's 3/3 plus 1/3 would be 4 pi over 3, is also going to be that same point that we started with. And similarly, we could come around in a negative angle and also use a negative r value. And so that would be, see, 3/3 minus 1/3, that would be a -2 pi over 3 for the angle, and a -2 for the r would still be that same point. And so you can see there are infinite numbers of ordered pairs to represent that one single point. Okay, so let's talk about coordinate conversion. So I have here an xy axis, and well, a lot of times we will draw our polar coordinates, the point, or we're going to get to equations and curves here in not too long. We'll still draw them with an xy axis as well. So this r and theta just lend themselves very well to, like what we have seen before in our trig days. If we drop the perpendicular, we create that that reference triangle, and this distance is x, this is y, we have the r and the theta, and so we have that relationship between them where we know that, let's go with cosine of theta, we know is adjacent x over the hypotenuse r, which leads to x is equal to r cosine theta. So if we know the r and the theta, this is how we're going to find the x. Similarly, sine theta is going to be opposite over hypotenuse, and that is going to lead us to y equals r sine theta. So these are the conversions from polar to rectangular. Additionally, we can go the other way. So if we knew what the x and y were, we could say that the r, which is the hypotenuse in that right triangle, is the square root of x squared plus y squared. Likewise, tangent of theta is y over x, opposite over adjacent. So that means if we solve for theta, we get that theta is the inverse tangent of y over x. And so those are the formulas that we are going to use, if you will, to convert from polar to rectangular or rectangular to polar. So let's see if we can find rectangular coordinates. So let's find rectangular coordinates for the point, say, 3, 5 pi over 6. So we know that x is going to be r cosine theta, which our r is 3, and our theta is 5 pi over 6. Now sometimes this is going to mean we're going to have to use our calculator, but we actually know 5 pi over 6. Reference angle is pi over 6. That's going to make the cosine square root of 3 over 2. Because we're in quadrant 2, that's going to make that be a negative square root of 3 over 2. And so we're going to get a -3 square root of 3 over 2 for the x coordinate to that point. Similarly, the y is going to be r sine theta, which is going to be 3 times the sine of 5 pi over 6. And sine of pi over 6 is 1/2. In quadrant 2, sine is still positive, so that's going to make that be 3 times 1/2, or 3/2. So our rectangular coordinates are going to be -3 square root of 3 over 2, 3/2. So if we go the other way, let's take a point that is in rectangular. say -1, comma 1, and let's convert that to polar. Now, I'm going to draw a picture here real quick so we can kind of visualize what's going on here. So we're at -1 and 1. We're talking about this point that's in quadrant 2. Now, if you imagine making that right triangle, I think you can see that that reference angle is 45 degrees or pi over 4, which is going to make that angle be 3 pi over 4 without having to do like an inverse tangent. We can see that the r is going to be the square root of -1 squared plus 1 squared is going to make that be square root of 2. Now, there are actually many different versions of these polar coordinates. So one version would be square root of 2, comma 3 pi over 4. And if all I ask you is for one pair, that would be okay. Sometimes I'll ask you to find all of them where theta is going to be between 0 and 2 pi. Let's go from -2 pi to +2 pi. So if that were the case, we're going to get two different ordered pairs that have that r value that's positive, and then we're going to get two others where the r value is negative. So if we're going to stick with a positive r, then our other angle is going to come around in this direction. And so that's going to be a -5 pi over 4. Now, if we choose a negative r value, that means we need to find an angle over here. And so if we choose a negative square root of 2, then one option would be to choose a negative angle there, which would be a negative pi over 4. So the negative pi over 4 takes us to this green angle, and the negative square root of 2 shoots us through the pole and back to our original point. Likewise, we could do negative square root of 2 and choose that positive angle, which I believe is going to be 7 pi over 4. So there are 4 versions of those ordered pairs, those coordinates, polar coordinates for that rectangular point, -1, 1. Okay, I'm going to get a new screen here. And we can also do equation conversions. So we're going to still refer back to these conversions that x is going to be r cosine theta and y is going to be r sine theta. And we're also going to get that r is the square root of x squared plus y squared, and that theta is going to be the inverse tangent of y over x. The more you do these, the more you just remember them. So here we have this r equals 4 cosine theta. This is kind of a tricky idea, this equation conversion, because you don't do the same thing necessarily all the time. But what we want to do here is get from the r's and thetas into x's and y's. So we would like to create these r cosine thetas and r sine thetas if we can. So in this case, I can see that cosine theta sitting there by itself. So I'm going to multiply through both sides of the equation by r. And so that is going to make that be r squared equals 4r cosine theta. Now this is great progress because we know that r is the square root of x squared plus y squared, which we have now squared. That's good news. And we can hopefully see this r cosine theta is going to become a 4x. And so what we've got is x squared plus y squared is equal to 4x. And I'd be thrilled with that. Now, looking at the other one here, this rectangular to polars, now we're going to try to get rid of these x's and y's. So what I'm going to do in this case is call that x squared r cosine theta squared minus 3, and then we get an r cosine theta for the x, and then plus an r sine theta quantity squared for the y squared, and a 5r sine theta for the y. Now there's other ways of doing this too. Once you get good at it, you can sometimes be efficient. So I don't know if any of you maybe noticed you could see the x squared and y squared could combine to become an r squared, which would be great, but I'm going to go there using a few more steps. So this is going to be r squared cosine squared theta minus 3r cosine theta plus r squared sine squared theta plus 5r sine theta equals 0. Okay, I think I'm back. I hit the wrong thing there. So eventually we want to get to r equals, our goal is to get r equals something with thetas in it. So we can, if we like, because everything's got an r in it, we can divide through everything by the r here. And that's going to bring us to r cosine squared theta minus 3 cosine theta plus r sine squared theta plus 5 sine theta equals 0. So I'm going to keep these together because they both still have an r in them. So, and I'm going to move the others to the other side of the equal sign because I'm seeing something with this sine squared and cosine squared. Moving the minus 3 cosine theta to the other side makes it positive, and the 5 sine theta becomes a minus 5 sine theta. Now, I don't know if you see it, but if we factor this r out, we're going to see our most famous of all trig identities, our personal favorites. That is, we're going to see sine squared plus cosine squared theta, which we know is 1. And so that makes that r times 1. And so we get, this is actually our answer because we have r as a function of theta. R is equal to just a bunch of stuff with thetas in it. Like I said, this can be a little bit tricky. Okay, I'm going to stop here.